I'm Robert Virding. I work at a company called Erlang Solutions, and we do consulting and training in and around Erlang, and also have some products. This is more a private project I've been working on doing, and it's an implementation of Luerl on the Erlang VM. So what I want to talk about a bit here is why Erlang in the first place. So a little bit about the problem, what we're trying to solve, and some of the properties of the Erlang language. I won't go very deeply into this at all, but the properties of the language very much affect implementing other things on top of it, including Luerl. So the system I call Luerl, what was the goal of it, the results of it, a bit about the implementation, a small demo, and some comparison about doing this in other ways. So that's my target. So why Erlang? The problem we're trying to solve is that way back, Ericsson had a switch called AXE. They still have it. Very good switch. But it was difficult to develop and maintain the software of it. So I was working at the time in a computer science lab in Ericsson, and one of the things we were looking at is how we could simplify this process of developing and maintaining these types of applications. So what is the problem domain? What are some of the properties of these type of applications? And number of the basic things we arrived at here was that, or rather then, was that you need lightweight, you need massive concurrency. You typically have a lot of things going on in the system at the same time. I mean, if you're talking of a large exchange, you might have a few 100,000 lines in, you might have tens of thousands of calls going on at the same time, plus everything else the switch is doing. So you need a lot of concurrency in the problem. The systems have to be fault tolerant. So when things go wrong, the system must not crash. It must be able to keep on going. We have timing constraints. Things cannot take too long time. They have to happen at a certain time, and all these type of things for it. That means, for example, the system must never block. You must always be able to provide low latency. The system must never block for anything. Continuous operation over a long time. These things should run for a long time, and you should be able to do maintenance and evolution of the system while the system is running. You should not have to take the system down to do these type of things. So one of the guys who started the development of Erlang, Joe Armstrong, he said the system should never go down, and he was asked what is never, and he said less than 4 minutes per year. And that's probably a bit too much, actually. So that's the type of things we're looking at. And you need to be able to do distribution. So if you want to truly build a fault-tolerant system, you need at least 2 computers. There's just no way around that. Therefore, you need some form of distribution so they can interact and work with each other. So these were the type of things in this problem domain. And these things, they aren't optional in the sense. If we developed a system which couldn't do this, then it wasn't interesting. So these were sort of requirements for the system itself. They very much influenced what came into Erlang, what didn't go into Erlang, and things like this for us. So some points I want to stress here. I don't know if much people know about Erlang, but we were not actually trying to implement a functional language. It became functional as we were working. Someone came along and said, you've implemented a functional language, and we sort of said, have we? Oh, well, great. We were not trying to implement the actor model. So people say, yes, Erlang implements the actor model. When we were developing Erlang, we did not know about the actor model. Okay, the actor model is older than Erlang, we had just not read the papers. And we read later that someone said, Erlang implements the actor model. Then when we looked in the papers, the description of the actor model, and we said, we've almost done that, yes. What we were trying to do was solve the problem. We had the problem with these requirements, how we're best going to solve it, and we ended up with what is now Erlang. So just some more around this. This actually made the development of the language, the system, very focused, because we knew exactly where we were going. We knew exactly what requirements we had, we knew exactly where we were going. So we knew what was necessary to put into the language and into the design of the systems using this language. So everything worked together. So the language design while we're developing the language, we're also looking at how we would use this language to build these type of systems. So everything worked together here. And we had that gave us a very clear set of criteria of what should go into the language and what should go into the system. Basically, was it useful? If it wasn't useful, don't put it in. Did it or did it not help build systems? The same thing there. So very clear criteria for it. And that made it very easy to keep things out. And it kept the language and it kept the way the systems were built very clear and very concise, which is a nice feature. That's by the way, one of the things I like about Luerl. It's a very small, sharp little language doing one thing. It's got a very powerful small set of tools, a small set of very powerful tools which allow you to do a lot of things with it without having to put a lot of stuff into the language to do things. That's what we're trying to do at the same time with Erlang, and we've more or less succeeded doing that. So again, the language and the system evolved to solve the problem. So we knew the type of problem we were going to solve. That's what determined what went into the language and how the language was used to build systems. So again, we weren't out to make a functional language, we weren't out to implement the actor model. We arrived at those solutions as a good way of solving a problem. So where did we end up in the Erlang system? So these are a set of things that you'd find in the basic system. We do provide support for massive lightweight concurrency. Asynchronous communication is the best, the base of everything. I mean, if you want to make a non-blocking system, you cannot do synchronous communication. Just forget it, right? We have processes and we have process isolation. So what we have internally in our Erlang system are processes. That's how we implement the concurrency. They are isolated, they're not like threads. This works together with the error handling mechanisms. We can happily crash things inside Erlang without taking the system down. We provide support for continuous evolution of the system. Yes, we have support for soft real-time. We're not hard real-time, but we have support for soft real-time. For example, the system will never stop very long when it's doing garbage collection. We have different ways of doing that. We also have a lot of support for introspection and monitoring of the system while it's running. Again, this is getting back to the case where you have a long system, production system running on Erlang. While the system is running, you have to keep track of what's going on. Is it doing strange things? So you need all these primitives for looking at the system while it's running. These are things you seldom have to worry about if you're implementing languages on top of Erlang. They're a base as part of the system. But they very much affect everything else. Everything else works together. Everything seems to work together here. So some other properties of the language. Now we're getting much closer to what we see is all data is immutable. There is no immutable data at all in the system. That affects a lot. We have support for pattern matching. It's a functional language. We only have a predefined set of data types. We have a predefined code handling structure. We have modules and how they work. That's very well predefined. We don't have global data at all. We just don't do global data. We don't share anything. And this again very much affects how you build systems on it. So these are some of the properties of the Erlang language and the Erlang system around these things. I won't go into more of them here. If people have questions, you can take it later. But this is also very much affects how you implement things on top of Erlang. So the actors, the concurrency, the lack of global data affects how you structure systems, how you build your systems, which is very different. These features here, like immutable data, for example, very much affect how you implement Luerl on top of Erlang. So that's a bit about the Erlang system. So what the goal of Luerl, it was supposed to be a proper implementation of the Luerl language. Okay. In the sense that it should look and behave as Luerl does. So I should be able to take a program written in Luerl, run it on Luerl, and it should do the same thing. That was the goal. We should also be able to include all the standard libraries. So you should get what you expect, right, when you run these things. And it should interface well with Erlang. Otherwise it'd be an interesting experiment, but it wouldn't be usable. Not from the Erlang point of view anyway. So they were the main goals of it. The result, well, we implement almost all of Luerl 5.2. We don't do go-tos. I could probably do them, but I couldn't be bothered. To be honest. And I don't like go-tos anyway. And no one seemed to complain so far anyway. Luerl doesn't handle the environment as it should. It's basically based around _G now, and that works, right? If someone actually wants the environment handling, I can fix it. I know how to do it. I just haven't done it. And we haven't done coroutines. Again, no one said anything about this. I know they're useful. I've heard some talks from this morning. But we would do that using Erlang processes anyway, so not right. It seems to manage all the tests. I've got a test environment there, except for the ones that use the debug module. Because one of the things I don't implement is the debug module, because that is very implementation specific. So yes. It does interact well with Erlang. So it's easy for Erlang to call Lua, and it's easy for Lua to call Erlang backwards and forwards. And it is compatible with the Erlang concurrency model and the error handling. So I've got a simple example afterwards. There is one problem with implementing Lua on top of Erlang. You have to be aware of that the way Lua handles code is not the same as the way Erlang handles code. Both can do code upgrades on the running system. That's not the problem. But they do it in different ways with different requirements. Amongst other things, so for example, on Erlang, you can have at most 2 versions of a module in the system. So if you try to load in the third one, you're going to start killing things, right? Which is not the same as Lua does. So you have to be very careful when, if you're reloading Lua modules that might reload Erlang modules, you might get strange behavior if you're not careful about this, right? So this is just one feature. So we implemented the libraries, basically all of them except the debug library. I did very little in the IO library. It's just that it wasn't something I needed. I can write things out, that's about it. And some of the operating system facilities. We do the packages, the module handling, the packages, but not the C code version of it. Because again, that runs into a lot of problems with how you're going to do C code through Erlang. I think there was one of the string functions I did not do that seemed problematic for it. But, everything else seems to work. The funny thing was the mathematical libraries, or the bitwise operations, by the way, because Erlang supports dynamic size for integers. They can be any. There's a big num package built into it, so you explicitly have to go in and limit things to 32 bits when you're doing these type of bitwise operations. But otherwise, everything seems to work quite well. The programming interface, the Erlang interface is very straightforward. There's an Erlang library which lets you call Lua. Lets you call Lua from it. It lets you set up a Lua environment, lets you evaluate Lua functions inside it, create and access tables and things like this for it. It doesn't implement everything, but it's quite easy to add something necessary. And it's quite straightforward to call Erlang from Lua as well too. So you can define a Lua module, a Lua table, which interfaces calls Erlang functions. And you can write special interface functions for doing things. And it's quite straightforward to do it. We don't have a direct C interface though. It's just difficult to do that. So the implementation. One of the goals here with the Luerl system was that everything should be done in Erlang. We should not require something written in another language or another system to do it. So, amongst other things, we want to be able to parse Lua ourselves. And that was actually surprisingly simple. So it's basically the Lua grammar, I don't know if this was done on purpose, but it's almost LALR1. There's one small thing that isn't, but it's quite easy to get around that.
What is it?
I can show you later. If you show me the grammar, I'll show you what it is. Right? There's just one thing in the grammar that you've got 2 left-hand sides which are almost the same, but then they do something different in the middle, and then the grammar can't choose which one. So you just make a general case, and afterwards you check and see which one it is, and do some extra tests. If it's on the grammar, it's about the 2nd or the 3rd grammar rule there that was causing the problems for it. But that was very nice, because that meant I could use some standard Erlang tools for doing this. So there is in the Erlang system a tokenizer generator called leaks, which I could then use to generate the tokens. And there's YEC, which is an LALR1 parsogram generator, which I could use for that, except for this one conflict. And you just handle that by doing the general case, then calling afterwards and see which one you get and do some extra tests for it. So it's very easy to do that, which was nice, because that solved the parsing problem, which can sometimes be very problematic otherwise. So that was easy. The implementation, it's a virtual machine, yes. It's relatively similar to the standard one, but it's not quite the same. There are a few other things that affect that. It's quite a straightforward machine. It doesn't do very many smart things. The compiler, of course, generates for that, and it tries to optimize things like environment handling, for example. So it detects which local variables are actually purely local and which have to be globalized, because they can be accessed from other environments. And it separates these because of the way the environments are handled. A lot of unnecessary information is compiled away, which, for example, makes the error messages pretty primitive. For example, if I want to call the function foo.bar and apply that to some arguments, it will find the table foo, it will find the bar key for that and get the return value, then try to call that as a function. If that happens to be nil, it will just say that I couldn't call the function nil, and it will just happen to have lost how it got there along the way, which makes the error messaging a bit simple, but it works. It does what it's supposed to do, but it works. One time I might get around to trying improving the machine to handle those cases. Data types, they match surprisingly well. Here again, I mean, Luerl has a fixed set of data types. They match quite well onto this. So the Luerl nil just matches onto the Erlang nil, the Erlang atom nil. Now, the Erlang doesn't have a concept of a nil at all, but I could use the Erlang atom nil and work around with using that. Luerl booleans just became the atom's true false. Numbers just became Erlang floats, and strings just became an Erlang data type called a binary. That was very straightforward and everything worked. That was no problem. The problem, of course, with tables, which they're a mix in my implementation of using Erlang arrays, or an array package on top of Erlang and a dictionary package on top of Erlang. So using the arrays when you've got the integer keys, and otherwise you're using the dictionary. And that works quite well. So far, so good. The problem is Luerl state. And this is the main difficulty in the implementation, that I need to implement mutable global state using immutable local data. Right? That is the problem, because all Erlang provides is immutable local data. I don't have anything else. Yes, I could have implemented something in C and put a library in C to implement the Luerl state, but then it would have been pretty useless. Then I might as well have taken the Luerl implementation straight off. Right? So this was the goal, to keep everything in Erlang. So the way we do this is we keep the complete Luerl state in one data structure, which you then thread through everything. So when you make a call into the Luerl system, you pass in a state. The Luerl system internally will thread this state through, making changes to it, then return back the value which I can get the next call. Makes things a bit complex, but it's quite straightforward. From the Erlang point of view, this is what you normally do anyway, right? Here we're just passing through another structure. From the Erlang point of view, implementing Luerl, that's just running normal Erlang functions. So Erlang doesn't, in this sense, see that we're implementing another language, it's just running code. But it makes things slightly more complex for it. So what we need in our big data structure, we have a global table store. Here we run into problems. I mean, I cannot have a local table, say, in the stack, because then that is purely local. And if I modify that table, then no one else will see the modification. So I have to implement a global table store. It's a big array containing tables. I reference each table through its index. Any changes that are made into that global table. I need the same thing for the environment frames that are global. So I need a table to keep track of all the global environment frames. So when I modify those, everyone will see the changes. Everyone needs access and will see the changes. Because again, if I only make local changes, only I will see the changes. That's why the compiler gets quite a lot of effort into separating truly local variables from truly environment variables. What's happening now? Didn't like me. Wait. There we go. Have to be careful. Let's see if it comes up again now. Nope. I think I stood on something. Oh.
Maybe?
Maybe? Yeah, there we go. I'll just be careful where I stand. Excuse me. It's the same thing. So I have to keep an explicit global store of things, and everything that uses those are just references into that store. The same thing with environment frames. I keep a stack of tables. I also need to keep the current environment stack, the execution stack in there as well. Because it's all state here, and I can return that and come back again. And on top of this, I actually have to implement my own garbage collector. Because what is garbage? Well, it's not what's in the tables. They might be now no longer used by the rest of the Luerl system. So I have to write my own garbage collector, which runs through and does these type of things, which does feel a bit strange actually. And then I just hand over stuff to the Erlang garbage collector, which cleans up. So yes, so it works. This is just an example from the Erlang side. This is just showing this is the top one here, the top record called Luerl there, is actually what's in the Luerl state. So the top three things are the tables. They're the tables. It's a table array. It's a list of free elements in that table, because that's how the array works. And if I run out of free elements, it's the next element number to use. And I have the same thing for the frames. G is the whole global table there. We've got the current stack. Meta, just the meta types, meta tables for the various predefined data types here. So if you look down the next one, you see there's a meta table. There would be the meta table for nils, booleans, numbers, and strings. So the bottom case here is if I've got a reference to a table, what this is just an index into the table array, saying I want table 39, that's the table I'm working on now. And the same thing with the frames. The table here has 3 fields. It has an array. That's what's called A. I like short variable names. Okay. So that's just the array for the indexes. The T is the table for the other keys, and M is the meta table. So these things. So this is basically what the data structure looks like internally. Okay, this is just a lot of Erlang code showing how you actually access the table. I will skip. If anyone wants to see that later, they can come by and I'll show them. This is the real code, by the way, from the system, of what you need to do to go find things in there as well. So I'll just skip over that. Yeah, I have a demo. Okay, now, this is probably the wrong place to show a demo with games, because my gaming demo is not very much to see, but it shows some of the features of the system. So we'll put this down for a moment, and so I can see something. So we'll start up a system here. I've got an Erlang running here, and I'll run up a little space here. So we'll start the system, and it's a bit of a universe here, and I'll run 1,000 ships on it. So that's opened up the universe. Now we need to show the ships here, and then we need to start it. I'll say 75. That should be enough. This is just saying how long a clock tick is. The 75. So clock tick 75 milliseconds. So now we've got 1,000 ships running there, right? And you can actually see them. They're not that big, but yes. And these are very simple ships. They just run in a straight line until they hit the edge of the universe, and they bounce and come back up again. So that's not exciting. But we can do other things here. We can say, now we're going to use the Luerl feature of loading in new code. So now I'm going to say some of these ships, they're pretty timid, right? So we'll call them a timid ship. And I will say the first 100 of them are timid, right? Let's see, bump, 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 there. And there we see some of the ships have actually turned yellow, right? Because they're scared. So if they're going forward and they see another ship in the sector in front of them, they go yellow and they go back the other way until they bounce and to hit the wall and bounce. They're a bit hard to see. Yellow's not a good colour, but there are a couple of them, for example, wandering up to the right. You can see them there. When they hit the wall, they hit the edge of the universe. They go white again. So we have some other ships we can add as well too. So we can add something called these are called run ships. So what they will do is you'll see when they start running. So we'll start up a few of these. We'll start up from 100 till we'll make 600 of these. Now if we look here, so now what this set ship has done is actually loaded in this code into this case 500 ships. And you see the ones that are going green on that, they're the set ships, and they will eventually start going towards the edge of the universe and then circling around the edge of the universe. You can see that happening with the green. You can't see the bottom of the universe, I'm afraid, but it's down there as well too. And we've still got our yellow ships who are scared and things like this for it. So we're doing these. And as I said, we've actually loaded in the code, the set ships code, dynamically into these 500 machines. And we've got 100 machines running timid, and we've still got 400 machines with traditional white. So there's just one thing more we need to do here. This is gaming, of course, and we can't have a game where we don't kill things, right? So we'll make some attack ships. So we can do this, and they will be red, and we'll make 100 attack ships. So they'll go from 600 to 700. And we'll still have 300 left of the default ships. Yes. Now they'll be red. And so the little white, yellow squares there, that's explosions. I'm not really into graphics, okay? That's explosions. Well, what the red ships do is when they go forward and they see another ship in front of them, they kill it. And that's the explosion you're seeing here. So now they're doing, and what you actually see on the right-hand side is the ships dying. Each of these ships is an Erlang process. Each of the ships is running its own Luerl system, Luerl environment for it. So we get going on here. We can just let this keep going here, zapping stuff, and we can get back to the talk. So that's the demo here for it. So yeah, so logic is in Luerl. Each ship is an Erlang process, and they're communicating between the ships by sending messages through the Erlang system. So when you zap a ship, you send a zap signal to it, it dies, it prints out it's yellow, then the Erlang process dies. So yes. So I have some demo of the code here, just very simply, we'll just look at bits of it I think to go through here. So every clock tick, a move function is called. And this is the move function for the default ship. It calls the function move x, y, bounce. That's the one that just steps it one step forward. So x and y are the current positions, dx, dy, they're just how much we move it per tick. And then we can just check if where we're going to is a valid position. And then we just get the sectors of the universe where we are. And if we've changed sector, then we just remove ourselves from the old sector, add ourselves to the new sector, and redraw ourselves. That's what this does. The bounce x, y just increments x and y to new values and just checks if x is valid, then we'll go ahead. Otherwise, we'll bounce and go backwards. Same thing with y here. So this is the default ships that just go straight ahead and move. This is the move for the attack ships, which is almost exactly the same. They move in a straight line, but the difference is about down the middle here, where we go out and call the zap ships function. That's the one that checks if things are close to us and kills them if they are. Otherwise, we keep moving before. The zap ships now, well, that calls a function called move LR sectors, which just works out the sector where we're going and the left and right of that sector. So we can work out these things for it. And then I just get a ship out of the sector where we're going, which is the NX and SY, and if there's one there, I zap it. That kills it. And then I check do I have a ship on the left or on the right. If I have one of those, if I find one, I'll zap that as well too. So that's all the attack ship does. Just keeps going straight forward, and when it gets close to something, it kills it. This was actually the most complex one to write. It's the general thing. If I'm going in one direction to one sector, what's the sector on the right of that, and what's the sector on the left of that? That's what these does, to test different values. And yeah, so this works. This is a very nice way. It's very Erlang in this sense, because if the process dies, the Erlang process will die as Erlang processes should, and everything works like this. From the Erlang point of view, it's very simple. It's just a data structure we're manipulating. It means, for example, I can have multiple Luerl states and run them in one process, one Erlang process. I can just flip between. If I want to do this, I can flip between them. So this coupling I have to a Luerl machine or Luerl state with an Erlang process is very up to me how I want to do that. So it's very versatile to do that as well too. But there are other ways of doing this. And another way would be not to run Luerl inside Erlang, but interface Erlang to a Luerl system outside. Say to a standard Luerl machine, I could send commands to it and do things through that way, through something Erlang has called a port. Or I could actually include the Luerl engine in the Erlang system and call it through an Erlang function, or the NIF, which we call C functions. So there are two alternative ways of doing this. So why pick one or pick the other? So Luerl and Erlang, it gives you complete access to Erlang and to all the VM properties you want from the Erlang. You're running Erlang, I mean, from that point of view, it's no difference. It's very easy to use the Erlang concurrency. It provides a very fast interface for passing data, because it's just the Erlang data going backwards in the output. And one benefit, perhaps, is I only need one system. I just need the Erlang system. I do not need to have multiple virtual machines to keep track of these things. Some downsides is it is slower. Yes, because it's not only the actual machine implementation, but I'm implementing data, and that costs. There's just no way around that. Measurements, some simple measurements I've made is that it's about 2 to 5 times slower depending on what you're doing. And most of this I'm suggesting is in the data access. Data sharing is difficult. Erlang does not share data. We have our processes, each process has local data, that's it. So if I want to share data, I have to send things. I'm slightly faking it in my system, but I pay for that as well too. So why would I use an external Luerl system? It's faster, definitely. No doubt about that. I'm probably able to run more Luerl code in the external system. There's no guarantee I can run it in mine. I haven't found something that doesn't work, but that's no real guarantee for it. The downside is the interface will be slow. I'll be sending commands across to the machine telling it what to do, which will be slow. It's more difficult to use the Erlang concurrency. I can do it. I can have multiple processes sending requests off, but I can still only process them once. Maybe I can start up a number of Luerl systems, and I can route requests to separate ones, but it still makes it much more difficult than it is now. And it's much more difficult to get the parallelism. One of the things the Erlang system does is it quite well uses the existing parallelism of the machine. So if you're running on 8 cores, you happen to use all 8 cores and it'll balance over them. If you're running 16 cores, it will use all 16 cores without any problems. There's nothing I have to do as a user, it just does it. So now I'm running my space here on 4 cores, or 8 cores actually, depending how you want to view it. And it's just something that just happened. Yes, I could start up specific Luerl machines, but it'd be more difficult to do that, to get the parallelism out of the system. So which one depends very much on what you want to do and what properties you're after. And that's about it. So thank you. Any questions? One.
Is that your process of communicating messages?
Yeah.
Is there a library like available in Luerl and binding for messages, or messages emitted for every assignment of a variable, or?
No. Okay. There is. I have not written a library, but I'll fix one this afternoon if you want it, right? No, seriously, it's not much more than that. What's being done now is that each of these processes has a top level, which is Erlang, and with a clock, then the clock ticks. And when the clock ticks, it calls a Luerl function for each one, the tick function, which then calls the move and does the moving for it. And there's another set of predefined interfaces. This is just this way of doing it. If I found this was easier for my demo. But there's no problem implementing a Luerl module which calls Erlang. For example, it has a send function and a receive function for getting messages. There's no problem doing this. I haven't had the need for it and haven't done it. But it's the same thing with interfacing everything else, right? You can just write a library if you do that. I mean, all the standard libraries are implemented in Erlang. So there's no problem doing that. And the interface is pretty well defined how you want to do it too. So, well.
You said in your implementation that you represent tables and almost everything by indices and lists.
Well, no, I have a dictionary. I've got an array for the numerical ones. For the one.
No, I mean in the state.
Yeah.
Each table will have a reference to, in the list of tables.
Yeah.
Is this a linked list or?
I keep it in a big array. It's a big array actually.
Oh, okay. So, but it's an immutable array.
It's an immutable array.
And how do you do updates?
I mean, you
create
rebuild bits, but
you rebuild
not all of it, but bits of it anyway. So it's a tree structure. It's a tree structure where you're working on three things.
And
So
that's standard in Erlang.
that's standard in Erlang. So it's one of the Erlang libraries that does this. There's come a new Erlang data type called a map, which would help a lot here, but they're missing one thing. There's no next, which makes it difficult. Right? And I tried to point this out, and I say, yeah, but you get a list of all the keys and then step down that list, but that's not something you can do every time you want to call next, right? It's not reasonable. I have to push them a bit more for that. But otherwise, that's our stuff. So.
You mentioned that you have a Lua VM. Is that just the Erlang VM, like you are compiling to Erlang?
No, I'm not compiling to Erlang. I've defined a Lua virtual machine. It's quite similar to the one in the standard, but it's not quite the same.
Lua bytecodes?
Yeah, they're bytecodes, and I have an interpreter doing those. It wouldn't be difficult to generate Erlang code, but then you hit the problem of the code handling. So now I can quite happily reload a Lua module, or Lua chunk many times, because from the Erlang point of view, it's just data. If I convert that to Erlang code, then I'll be reloading Erlang code, and I'll suddenly hit all the Erlang code requirements for, or restrictions for. For example, I can only have two running at the same time in one system. So I chose to do it this way to keep that, so I can keep the Lua side of it more normal Lua. So, yeah.
You said they have an explicit representation for the stack, for the Lua stack.
Yeah.
So it shouldn't be difficult to implement coroutines, I guess.
No, it's just I haven't done it. That's all. Really,
It's
no.
nothing.
Yeah, I don't see any problems doing it this way. I don't think so. The fact that they're coroutines, you basically only got one thread of execution, really doesn't make it much difference. So, and then again, I think I have the Erlang processors. I would use those if I want the concurrency. Okay, if I was running a Lua program which uses coroutines, then I didn't use those. I don't do that. Yeah.
Are you planning to implement at least a useful subset of the debug libraries, such as the get metatable and set metatable functions?
Don't I already have those?
Yeah,
Which library?
the
Which?
debug version, which gives the metatable field, which basically allows you to retrieve metatable from any table, even if it's like forbidden for the standard function. So there are versions in the debug library which are
Yeah, no, I've just not implemented debug library at all. Perhaps I could probably pick parts of it that I can do, but some parts I definitely can't
have you
do.
heard about the Elixir project?
Yeah.
What do you think about it?
I'm an Erlang person, okay. So from my point of view, I don't see the point. Because one, I don't know Lua. Oh, sorry, no, Lua, yes, I don't know Ruby. So the Elixir syntax, which is Ruby based, is to me completely foreign. Everything Elixir can do when it comes to building systems is based on Erlang anyway. So from that point of view, I don't gain anything. So from my personal point of view, I don't see any gain for me to do it. There's nothing that Elixir can do I can't do in Erlang. From that point of view, so. And to be honest, the Erlang language is actually smaller and simpler. It is smaller and more concise than the Elixir language. Okay. Nothing? Cool. Yeah. Here you go.
You said that you mentioned now again
Yeah.
about the debug library, a lot of implementation dependence.
Well, these things like I can get I can ask it the value of a variable. Well, yeah, but when I get down to compiled code, all the variable names are gone.
Oh,
A variable is just an index into a table.
but you should have that. I mean, you mean the global variables or local?
Local variables.
Oh, but local variables you don't need that. In Luerl also the variables can,
Yeah.
the names can go away and the debug.
Yeah,
Maybe I should.
just look at just things I've removed very much. Even the local variables that are part of the global environment, the names are gone, right? They don't exist anymore. They're just indexes. Yes, I could keep them. There's nothing saying I couldn't keep them. That's not the problem. I just don't do it. I suppose I could do more information. That's, for example, one reason why you get worse error messages. You get the right error message, but less information. I'm just saying you're trying to call the function nil, which you can't do, but it doesn't say how you got nil, and it doesn't even tell you the line number where nil wasn't on it. These things go away. It's just, yeah. Okay. Thank you. And, yeah, now there aren't many ships left. Most of them are killed off. The attack ships killed off each other, by the way. They just killed anything. We're indiscriminate. This is very Erlang-y. We don't care who we kill.